Great. It's really exciting to have Martin Casado here. I won't give him a long intro because I think most of you know him. And anyways, I want him to introduce himself a bit during the chat. But just very briefly, so Martin's a general partner at Andreessen Horowitz. He leads their efforts in infrastructure. And he's very well known in this community because he's one of the people who really got SDN going through his graduate work at Stanford and then starting Nicira and then VMware. So thanks so much for coming. It's great to have you here. I thought since there's at least one undergrad in this room, and so people may not know your story. I was wondering if you could tell us like how you got here, starting from back before you were at Stanford, working at Livermore, and what kinds of problems you're working on, and what motivated you to make this jump.
Yeah. So
push that little button. There you go.
Is this better?
Yep.
Hear me? Okay. Sorry about that. Okay. So here's the quick arc. I was actually a computational physics guy. I wasn't smart enough to be a theoretical physics guy, so I did programming. Is it not working, or?
It's cutting in and out.
Is it cutting in and out? Do I want to use that one?
You're good. You're good.
Okay. So what happened in physics, if you weren't smart enough to do the theory stuff, they'd have you do the compute stuff. So my first job out of undergrad was doing compute stuff, and I worked in the weapons program at Livermore. I was a distributed systems guy, so they pushed me to distributed systems. So you think a lot about state management and state consistency and a little bit of networking, but from the perspective of state management. So I was there, I joined in 99-ish, 2000, and 9/11 happened. And the weapons program was this kind of anachronism from the Cold War, right? Nobody cared about nuclear weapons. It was this kind of holdover from the 60s and 70s. And the whole tenor of the nation changed from nuclear weapons to the terrorist threat. And that was very much an information thing. So I happen to have all of these clearances. And so they're like, listen, you're a computer guy. You have all these clearances. We're going to move you into the intelligence service. So I actually went to the intelligence community. I worked with the CIA from 2001 to 2004. But I didn't really know networking. I kind of knew distributed systems and this and that. So I was I'm going to go to Stanford and take one class. So I took Nick McCune's CS244. That was my first networking course ever. That's how I got to know Nick. I was just some random dude that took these courses. But, we got along and we did some pretty good work. I got into the PhD program. And what was very interesting was if you're a distributed systems guy and you look at networks, especially back then, it was really silly. Because in distributed systems, you actually have a lot of trade-offs that you work with, like availability and consistency and state management. But when you move to the networking world, you didn't have any of those tools. You literally had the guarantees were it will converge. I can't tell you when, but it will converge, right? Or there will be end-to-end connectivity. I can't tell you when, but there will be. You just didn't have any guarantees because this technology was born out of the internet area, right? And so you had protocols and you had loose consistency. And so a lot of this SDN work started when I was there. I came from this distributed systems background, and we're wow, can you put stronger guarantees on state and state management and forwarding planes on these things? And at the same time, networks were being pushed into a bunch of different areas. Academically, there wasn't much enterprise stuff. At the time, almost everything was the internet. But data centers were coming up, mobile was coming up, the enterprise, Vern Paxson was doing great work on the enterprise at that time. And so when you're pushing networks into these different areas, in the past, they kind of solved all these problems, but they did it with not IP. And so now they had to resolve them all again. And so you had to kind of retrofit a better way of thinking about systems. So I worked on that, which became, a set of papers. There's a bunch of people working on them. As part of that, we were trying to abstract the system. We created OpenFlow. But that became kind of the body of work I did at Stanford, went off to create Nicira. And then, I guess the rest is history. I'm happy to talk about it if you want, but that kind of leads me up to somewhat modern days.
Could you say a bit more about, so you're working on these kind of security problems and what was your goal for how you would, build a secure network or, be able to take some policy or to take some behavior and implement that? Where was the gap?
Well, just put yourself in the perspective of someone that didn't know networking, right? And so I did a lot of operating system work, a lot of compiler work, a lot of distributed systems work, and it was mostly on convent systems, right? And so I was deep in the bowels of the intelligence community, and we were actually building custom operating systems. And so if I had a requirement for the CIA, their requirements were different than the requirements market forces would get you, right? And so you could encumber your users more. And so if we had a specific problem, we'd actually solve it in the operating system. We'd use Linux. Remember, SE Linux came out during this time and so forth. And then you can actually provide real guarantees because, well, at least in the case of an operating system, you're on the same machine, or if you're between operating systems, like at the time, distributed systems actually had pretty strong guarantees. Like maybe you're trading off a bunch of stuff. So you take someone that has that background and then you put them in networking. And so, let's say I wanted at the time to build, now these things seem silly, but you have to kind of transport yourself back about 25 years. So you take someone like, me, and you give them some networking gear and say, build a network where you have different communities of interest where you can guarantee that packets never go between them. And they're moving. So you just couldn't do that. Like the only way you could do that is have human beings manage state consistency, because the humans were putting the ACLs in. There was no dynamic way to do it. Now you could dynamically converge the routing protocols, right? So you could have some loose guarantees on end-to-end connectivity, but you had no guarantees other than Glenn running around putting ACLs in a switch or something like that. And often these two things were at odds. Like Glenn would go put the ACL in a switch, and then the routing protocol would route around it, for example. So you just have to put yourself in the mindset of someone that came from that background. And so a lot of the exercise, which is like, how can you actually have like more of a distributed mindset with like stronger guarantees on more control plane, not management, but control plane type stuff in networking.
Cool. By the way, we'll have plenty of time for questions. So if you have questions that follow on from a particular question we're discussing, we can do that intermixed. We can do it at the end as well. So I want to jump ahead. So you're a VC now.
I'm a VC now, yeah.
And you lead this infrastructure fund.
Yes.
Could you talk a bit about sort of what's that about? What things are exciting, and how is it different from the other kinds of investments that most VCs are thinking about these days?
Yeah. So what is infrastructure? So by the way, infrastructure is kind of not historically been a thing. It's just kind of becoming a thing in the VC space. So the definition of infrastructure is like the stuff you use to build the stuff. It's not apps. It's computer science abstractions. The users are technical. The buyers are technical. So the traditional pillars are compute, network, storage, databases, right? This is like the super traditional infrastructure. It just turns out it's a $3 trillion market. It's massive. And so my team only does kind of core computer science stuff. That is opposed to fintech, apps, consumer, many other areas.
And so can you speak a bit about, things that are exciting or things that you see as being disruptive?
Well, maybe I'll just focus on networking.
Yeah.
Okay, so networking has been boring for a while. It's actually getting kind of cool again, which is great. So it feels to me like networking is it's a service layer. So it's kind of drug along by like the workloads of the use cases. Like if the workloads change and the use cases change, then kind of the network kind of catches up to it, right? And so this is why, even for like my grad school work, we had the internet, we threw away all this great kind of enterprise networking technology, and then we had to kind of relearn it all on top of IP. And that was driven by the rise of enterprise networks, that was driven by the rise of data centers, and then we did a lot of work in mobile that was driven by the rise in cell phones, right? And I would say like a lot of like the network innovation in the last 20 years is that it's data centers and it's mobile and it's the enterprise. That's it, right? And then kind of nothing has really changed that until very recently. There's two areas for sure we're seeing a lot of change. The first one is space, which is super exciting. So LEO satellite, it's so funny. So I'm on the board of one of these space companies that does networking. Like you guys would all be gods. Like they have the most basic, it's like network in the 1970s. Like they don't have software-defined radios. These satellites are just bit pipes. They do the most basic type stuff, right? And that's because like the people that were building satellites to do networking in the past, it's like they were all these kind of holdovers from like the Cold Wars, like, Boeing and Raytheon, and like that's great, but like they just don't know networking. But now you've got like a huge refresh on all of these satellites, right? Now, very famously Starlink, but that in LEO, but like also in the geosynchronous space, you're actually having new satellites. And now they're like, oh, wow, like I'm putting my head up and I'm realizing that the entire industry's evolved a whole bunch. And so I'm going to actually do more sophisticated things. So you're actually seeing like stuff that we would all recognize in these satellites. I would say that Starlink is like a new ISP. I mean, the amount of connectivity is enormous. And so that's one area that we're seeing a lot of innovation. And the next one is all this AI stuff. Like it's kind of a weird cosmic, coincidence. I did some research early on with someone that's working deep in the bowels of one of these big research labs, and they are rebuilding the switching fabric to look like the old HPC switching fabrics. So those of you that are around long enough to remember like Qualtrics and MirrorNet, these were very, very different than the IP fabrics that we build today. I mean, they were these very special purpose, much stronger guarantees, much better cross-sectional bandwidth, much lower latencies. And we're seeing all of that come back again. And so we're taking, it's kind of like we had, the days of like these big HPC, they weren't mainframes. I'm talking like, like the 360 and like there was a bunch of like these kind of big HPC computers. We had these great fabrics for them. That all went to kind of Linux. And then we kind of took networking gear, which sucked, and then we kind of made it pretty good. But now we're going back to like the guarantees that you need to run like 100,000 node cluster. You actually have to get back to these HPCs. So now we're seeing kind of a refresh. And there's some very interesting work being done there. Unfortunately, it's mostly behind kind of like these kind of cloak and dagger-ish type, like everybody's so secret and there's so much money involved, but for sure we're seeing a lot of innovation. So just talking about networking, these two areas were very clearly, while networking has been relatively boring, we're actually starting to see a lot of new work.
Cool. One other thing related to infrastructure. So I remember a while ago, you were sort of tweeting about, the costs of the public cloud, and there's definitely companies, some people here working on private clouds and some large companies that are repatriating their data in compute.
Yeah.
Do you see that as a big driver of innovation, or is it just things have gotten so commoditized now that, a company can now sort of do this cheaper for themselves?
So is the question like, what is the state of repatriation roughly?
Yeah.
Can you guys still hear me? Okay, yeah. So what is the state of repatriation? So we had this kind of, we just did this study, which seems kind of obvious in retrospect, but it was really misunderstood. So maybe I'll just describe the study first, then we go into it, which is, so if you're a bank, Wells Fargo or Morgan Stanley, and you're doing something on-prem or doing it in the cloud, it doesn't really matter to your economics, because it's not part of your product, right? And so, you could do it on-prem, and that's very important because of like data governance, or you could do it in the cloud, and that's important because you don't have to have a big team. But like, if you look at the share price of Morgan Stanley, like it doesn't even register because it's not a variable cost. It's not something that you spend a lot in order to offer your good. On the other hand, if you're like a SaaS provider, an infrastructure provider, and your product is software, now, what you do with your infrastructure really matters because it's part of your cost of goods. It's actually part of your COGS, right? And so if you're, random, like I'm just say they have a lot of on-prem stuff. So, like let's say Adobe moves to the cloud. If you actually look at the costs to serve, like 50% of that is actually cloud costs, right? And then if you look at the share price is like a lot of it is indexed on what your margins are, what the COGS are. So we just did this very basic study that says for companies that offer SaaS offerings, like how much of their share price is a function of is a function of the cloud cost, just the cloud cost. And it turns out that these cloud costs, you could probably reduce it by half. And so if your share price, if you reduce your COGS by half, it would double your share price. I'm sorry if this is a little confusing, but it was a subtle point, but it's very important. So if you can double your share price and you're $100 billion company, right? That's another $100 billion in value that you can actually use in the company. You can take debt against it, you can offer it, etc. So it just turns out if you looked at it from the perspective of like a SaaS company, there was something like $200 billion that was just being consumed by the clouds that you could easily save by repatriating. It's very easy to make the economic argument to do that. And so we kind of wrote this paper that was like, for some of you big companies, if you brought it on, you save a lot of money. It's kind of funny. So a lot of them did. Microsoft got very upset. So Satya called my boss. Like Amazon called the boss. And it turns out if you actually sit down and just do the numbers, like even very mild opportunities because it's on leverage are incredibly meaningful. And so I think for like any new projects or like startups, none of this makes sense. I think if you're like a big enterprise company and you're not offering a software product, this doesn't really make sense because it's not part of your COGS. As soon as you're like, I don't know, Snowflake, for example, where like you're literally reselling infrastructure, you're either signing up to give away 30% of your margin, which is incredibly meaningful if you look at a stock price perspective, or you should start thinking about it. And since we've written that, I mean, unfortunately, nobody talks, but I've worked with dozens of companies that have actually either stayed on-prem or moved back on-prem for this reason.
And so, like, is there infrastructure work or businesses that are supporting this, or are these shops that are doing repatriation? You know, again, are things just so commoditized that they can just, you know, do what the hyperscalers are doing themselves?
Yeah, how do they do it? I mean, these things only make sense at scale. Like this makes no sense unless you're like a public company where your share price is based on your margin. It just doesn't make sense for anybody else, right? You just can't make the economic argument. But if your share price is based on your margin and the cloud is a portion of it, makes sense. And by then we have teams that are large enough to do it. And so I've seen every like version of this where like they will use third-party providers that offer it, they run it themselves, like the I mean, there's all sorts of models in order to do it. I think probably the most successful is often they'll just work with like a Dell or a large OEM, and they kind of, you know, do kind of more of an operating model, and they have third parties that run it, et cetera. I don't think that they do it in-house themselves, but it's a huge trend actually, and it still continues to be a huge trend.
Cool. So I wanted to shift gears a little bit and talk about open source. So we are an open source community, and I think we reflect sort of all the different parts of open source. So we have people coming from sort of a grassroots, you know, free software, free, you know, we're just put stuff out there and you know, random grad students will be able to build new systems. To we have companies that are participating in open source because they get value from the community and its assets, and also they can have discussions about how technology is evolving. So I think, you know, there's other facets as well. Could you talk a little bit about how you've used open source in your own companies, and you know, how you think about this as a sort of strategic asset for small companies and big companies, and what role communities like ours should be playing?
Yeah, open source is a very complicated thing. It's very, very complicated. I mean, and there's many lenses you can view open source by. I actually think one of the most accurate lens to view open source, it is the medium for which big companies have proxy wars against each other, honestly. And I really think that more than anything dictates the open source landscape. Like, I think that like Linux, you know, was more of a commoditizer to Unix than it was to Microsoft early on. And a lot of that, you know, was kept in check by IBM until it basically jumped the shark. I think like Android was basically a proxy battle against iPhone. You know, I think that MySQL was a proxy battle before Postgres against Oracle. And so what happens if the project is out there, the losing companies will, or the ones that are not market leaders, will support that in order to have a system of checks and balances. We're seeing this play out right now with Llama, which is, you know, the meta release, which all the people that are not kind of basically OpenAI, Anthropic are backing it. And so I think the most non-Pollyannic, legitimate view of open source is this kind of wildcard technology that ends up to being for strategic pieces, a proxy battleground for large companies. They're almost always resourced that way and so on. So I think it's very important. I think it's a very important systems of checks and balances, but it's very rarely an actual grassroots progressive things. I've almost never seen it that way. There's been a very interesting thing over the last 10 years about open source is that it's actually lost a lot of relevance. And I'll describe why. So in the era of shipping bits, like I ship bits to you and you run the bits, open source is very meaningful because I could ship you closed source and I could ship you open source, but like you have everything that you need to run it. Right? But that's not how we run software anymore, really. The way we run software these days is like we go to like some SaaS service and we use that SaaS service. And running a SaaS service is really hard because you're running a distributed system. And what everybody knows is like the only way to run a big distributed system is you have really smart administrators that know how to manage clusters, right? Like that's just the only way to do that. And then whatever operational tools that you have to help those people run those clusters, it's not going to be open source because it doesn't make sense. Because all of that operational stuff is going to be like deployment specific, right? And so, you know, it's fine that AWS is written on a whole bunch of open source. It doesn't matter. The reality is that the magic is these very complex, big distributed systems that are managed by these administrators who are very, very sophisticated and all their operational tooling. So you kind of ask the question, like, where does open source actually fit in this? Like, you can never, even if everything that AWS did, I'm just using that as an example, was open source, you wouldn't be able to run that service at scale. You just wouldn't, unless you could hire people that would know how to do these types of things. And so as software has moved into this kind of, like more of a SaaS service, the position of open source has changed quite a bit. And so, it's still highly relevant in dev tooling. Like, you'll never have a programming language on open source. Like, you'll never have like a lot of kind of like part of the dev tool chain that aren't. As far as like infrastructure services, most of the big ones tend to be closed source first, right? I mean, think about like the cloud data warehouse, right? Like, you have, Snowflake is closed source, it's huge. Think about data replication. You got Fivetran, which these are all like you have the closed source ones first, and then like people will try and commoditize with open source. But I think that like for traditional services, open source has lost relevance. Now, of course, we're not going to talk about AI until later, but like that is with AI, because a lot of it's run locally, like that is a little bit different, but it's just a different era.
So can you say a bit about like Nicira and OVS? Like that was an open source project that was important to Nicira, but how did that proxy war play out for you guys?
Yeah, I mean, so category creation is really hard. It's just tough, right? And so a lot of what you're doing is when you're building something new is you've got to educate the industry that you're trying to insert into. And you can't do that with words often. It's just like, it's not exact enough. And so in the case of Nicira, we did a lot of efforts that were just trying to educate on these principles and enable on these principles. And that was, open standards work. It was definitely a lot of open source work. And it was a lot of like talks and so forth. I think it's very hard. Here's one takeaway that's very relevant to this, which is if you have a choice of implementing an open source implementation or putting a standard or a spec, the one that's more powerful is always the open source implementation, like the default implementation of a spec, because that always becomes the de facto standard. Does this make sense? Because there's always some kind of quirky foible that people end up kind of working around and so forth. And so I think any new kind of category creation effort is going to have some open standard. I think because nobody's going to read an open standard and implement it, I think you need to release open source. And I think that open source ends up becoming the de facto standard, but that's not a product. It's literally just kind of an insertion path. So again, these things tend to be very, very important, especially, listen, if you're in the startup world, these things are incredibly important from a strategic standpoint. Because I lost all my Pollyanna because I was thinking, oh, I'm doing something for like the world. I'm going to put this out and people are going to love it. And then I realized that the entire ecosystem is dominated by big companies that hate each other. And then they use these as kind of ways of getting at each other. And so like I would, listen, open source is great. I think you need to view it with kind of Machiavellian mindset for which it lives in.
I want to pause there. Anyone have a question they want to ask Martin? Otherwise, we can talk about AI. So yeah, I think, most of us are not AI people. Obviously, AI is one of the next big disruption coming. What kinds of things are you thinking about right now in the AI space?
So who here is actually kind of following along at all? Are you guys like zero interest? Okay. So here's the good news. AI is a networking discipline. I'm 100% convinced, right? And for a number of ways. Number one, like Claude Shannon, information theory, did the first LLM. If you actually look like at the old paper, he actually did this, like I will, create an n-gram statistical way of like calculating the next token. So like it all goes back to Claude Shannon for one. For number two, okay, this is going to be this kind of oblique thing I'm going to say, but like just the implications are huge in the industry, which is the following. These models are very, very inexact, right? And so like, you put a prompt in it and then it'll spit something out and it may or may not be good. So if you're a programmer and you're using LLMs, you end up having to put in a lot of logic to like make them work. I'm going to give you through example. Let's say that you just want like structured JSON to a schema. So I'm going to put in some prompt to the LLM and it's going to spit out something and maybe the JSON doesn't compile. What do I do then? I kind of got to do a retry, right? So, okay, so now I'm going to have like, to do retries. Now, what if like that prompt will never spit out the correct JSON? Well, okay, so in that case, I'm going to have to actually sweep on that queue and like go ahead and eject stuff. What happens if I've got a whole bunch of these things that are calling this and the responses are streaming back and some of those stringing hang? Well, now I'm going to have to do some sort of keep alive. So if you look at any sophisticated code that uses LLM, any of it, it all looks like TCP. I'm not kidding. So it's been a long time since we as an industry have actually had a unreliable, non-deterministic substrate that looks like basically a wire. And these are exactly that. Not for the end-to-end like language logic, but like we have these things produce a lot of structured code. Like they'll produce JSON, they'll produce code, you can compile this code, you can compile the JSON. Not only that, you actually have these models now run tools. Like I could have a model like run like a web search, like a web crawl. That tool may not be idempotent. That tool may fail. There may be a sequence of tools that you have to run. So you end up having to implement sequencing, retries, quality of service, priorities, like all of the stuff that we've learned in networking you have to implement. And the thing is that people implementing this stuff don't know any of these things, right? So all the networking people, us that know this stuff, are off kind of working in a different part of the world. And then these like data scientists who don't know anything are like reinventing TCP horribly. So actually, just as kind of a lark over the last 2 months, I've looked at every significant implementation of these platform layers that they just basically say, programmer, use my API, and then I'll call LLMs for you, and I'll provide some guarantees. And if you open up the covers to them, they're all just horrible implementations of networking. So I actually think that there's a tremendous amount of opportunity for the people in this room to actually provide strong guarantees on like calling these models. Does this make sense? Does that make sense? So, and I will say, now again, I actually program almost every night with it because they are kind of magic. So if OpenAI gives you like an API to call an LLM, to write a system that actually works, it's like 95% networking code. By the way, networking code, I mean just literally all the stuff to provide end-to-end guarantees. Like there's a lot of stuff you have to provide end-to-end guarantees and then be able to clean up stuff. So that's like 95% of your code, and like 5% of the code is actually calling the LLM. So I do think we're just back at this kind of classically kind of networking-y era again. And then listen, on top of that, like listen, these things are kind of like this, they're pretty magic. They can do a lot of really neat things. And so I think it's evolving how people view systems. Like it's almost like it's almost another computer science primitive. And so there's a lot of opportunity for like the skill set in this room. There's nothing to do with AI. It's just classic systems work to be done. I remember when like seriously, I remember when like our TCP stacks, you'd like download from the web and run it. But this is different than that. I'm literally saying like, I mean, this is like an unreliable link, right? And so you have to provide end-to-end guarantees on this unreliable link. And then you realize that you have to do multiple calls in a certain order. So now you actually have to have sequencing, and you can have drops anyway. I mean, it literally is re-implementing a lot of networking. It's just at a much higher level.
So I have an angle with my professor hat on. If you go to any traditional CS networking or systems conference these days, you're going to find a bunch of papers that are basically, we took this problem, maybe it was solved with conventional means or using heuristics. We put it in an LLM and, we got it to do something. And then you have the skeptics who are kind of like, well, did you really, was this really an improvement or such? So if you think about sort of the space of not the things you build on top, but the actual, systems, things like database engines or compilers or congestion control protocols, where do you see, the disruption of AI with these kind of?
I think these are dumb, man. Like I hate all of these things. Like, listen, we've had predictive models for a very long time. What is a predictive model? A predictive model looks at a system, comes with some stochastic model and does a prediction. And what does it normally impact? It impacts accuracy, right? Like what is fraud? Like, should I drop a packet? Is like whatever. So there's nothing new about predictive models. But that's not what this AI stuff is. Like this new AI stuff is generative, meaning I put in a prompt and I get something net new. That's what generative AI is. So what would you guess the number one use case of generative AI is dollar weighted? Number one. What? What? Trading? Customer care? Right. Good. So the number one use case is creative composition. It is like creating content that's like a story or an image, normally for fantasy. And you can make a very strong economic argument for what this is, right? Which is like, if I were to create a Pixar character of Martine, like, and I would have a designer do it, how long would that take? I don't know, an hour and $100, right? As opposed to actually having like a model do it, which the inference cost is what, 1/100th of a penny, right? So you've got 4 orders of magnitude different. So when it comes to creating new content where there's no formal notions of correctness, like, you use generative AI. Those companies are working. So what do you think is the number 2 use case of Gen AI?
Picking stuff in an image.
But we've had that for a very long time, right? Which is so the number 2 use case, dollar weighted, is basically porn, but it's kind of this kind of weird companionship type stuff. These are very successful, solvent companies. So we've never, as an industry, have solved the emotion problem with computers. Like, you've just never been like, oh, I'm emotionally connected to my computer, I'm going to talk to this thing, it's real. And you just see the numbers for companies like Character AI. I mean, like, people spend twice as much time as there that they will on Instagram. It's a total, and like, by the way, we went through COVID, so we're all primed to do this. So dollar weighted, seriously, dollar weighted, number 1 is creative composition, so creativity. So it's, number 2 is this companionship stuff. And we're talking to chatbots and characters and whatever. Now, the one that's interesting about that one is that kind of this long tail of like, companies that are kind of on the border of not safe for work. And so like, you don't have a lot of traditional investors, like we don't invest in it or anything like that, right? But there's many out there, they're totally solvent, they're totally profitable. But these 2 categories are very different. When people talk about AI, they talk about what people said here, like it's customer service, which none of those things are actually really working. The stuff that's working are these totally new modalities. And today it's just not good at correctness. So you kind of want it to be out in these kind of new far-flung areas. So I will say, this reminds me, being old enough to be there, very much like the early days of the internet. The early days of the internet were like basically entertainment and like edgy, not safe for work stuff. Like, that's what it was. And I remember like, oh, you go on IRC and like, oh, you're talking to strangers. Oh, that's so weird, right? That was like Slack. It's like, like workplace boring. But in the early days of the internet, it was weird, man. I was like on FNet all the time. I was like on IRC all the time. Video games, oh, this entertainment stuff is going to rot your brain. Like, video games are going to kill us, right? Now it's standard. We're having the exact same moment of AI right now, but just realize that it's happening in very, very different domains than what we're talking about. And then there's one more thing, which is, and I was a super skeptic about it, but coding does seem to be really working. I mean, I don't know how much of you guys use like Cursor or whatever, but like, I'm a curmudgeonly old programmer. Like, I still use Vim. Like, I'm like a crusty dude. Yeah. But I do have Claude open, and like, I actually find that Claude is a great brainstorming partner on, especially like a lot of new languages. Like, I'm just getting like really into JavaScript and so forth. So for that, it tends dollar weighted is the number 3 use case. And so if you look from a use case standpoint, it's this other stuff. But what academics always do this is every time they come to, they say, we do networking, but with AI. And it's not even clear to me like how the AI applies to these traditional problems, and a lot of the predictive modeling we do does. And so I would say, if you're interested in AI, realize that it's in a whole new class of use cases and not the old ones.
So just to throw one thing out there, I mean, there are people proposing and some maybe doing, AI for different forms of discovery. So using it for math or using it for, discovering new substances and things like this. This is in universities, this is kind of all the buzz right now. That seems consistent with your view that, there's this different kind of problem we can solve, and it's not going to give us an exact answer, but it might help us with this kind of creative but faulty discovery process.
Yeah, so I think we can actually start to formalize a lot of this stuff. So like what was a really big unlock with Gen AI in the last 5 years? Like if you could just like abstract it at the highest level. Have you guys read The Bitter Lesson? You guys familiar with this? The Bitter Lesson is probably the most impactful. How every once in a while someone like writes like a crappy web page opinion piece that ends up like being like the cornerstone of like an entire industry. I think The Bitter Lesson is that for AI. It just says the following. It's very simple. It says, if you're building a model, don't be cute about the algorithms. Just do it in a way that you can scale compute, because you can always throw more compute at it. That's all it's saying, right? It almost reminds me of these kind of aphorisms you have with distributed systems, which it used to be like, you can make this very complex distributed system and make your program entirely unmaintainable and use threads and message passing and like whatever, and it'll take you 18 months and get 2x speed up. Or you can grab your towel and go to the beach for 18 months and get 2x speed up. Because so like it's the exact same thing that gets applied now to AI, which is don't be clever, just throw more compute. And as long as like your loss function scales with compute, it'll be better. And you should look up the bitter lesson. You should read that. But what it's allowed us to do is actually throw compute at problems that we otherwise couldn't throw compute at, right? You'd have to throw algorithms, etc. Now, conversation about AGI or whatever aside, this allows you to like, like AI is like basically a universal function approximator. So it just allows you to go into areas that we just haven't been able to, just because we didn't know how to write the instructions to do it, which would be how you do it with imperative programming. We didn't know what the formal solution is, which is how you do it with declarative programming. It literally is just saying, here's the data, we're going to throw some compute and answer. So I think it's going to answer a lot of problems that we couldn't, because it allows us to throw compute at that problem. But it's still very limited. So for example, if you're solving protein folding, whatever model you did to solve protein folding is not going to be good at playing chess, right? And so you've got general models that are trained on a bunch of text, and then you got very specialized models, but it does allow you to throw compute. That makes,
Yep.
Yeah.
So we have about 5 minutes left with Martine. So I really do want to open the floor to questions. Otherwise, I'll have to start opening up my generative AI and asking questions that way. Yeah, do you want to go to the mic?
So this is actually a P4 question.
Yeah.
So the intent of P4, I guess, has two parts to it. One is, the user expresses their, intent in terms of what they want to do, and also you want to enable operators to program the various network components. But one thing I have learned is that there is inherently a compile time notion built into this idea, right? That you have to have this compile time where you decide on certain things, and then there's also the runtime, when you operate, that you're also doing things, right? It seems to me that the P4 idea didn't factor in the runtime, and in fact, one of our customers, they're using P4 only for the parser, and everything else they are doing runtime. Your thoughts on this?
I mean, I think that's a totally legit observation. I mean, I think there's a huge contribution just to allow specification of the static aspects of a system, right? And I think that these things should naturally be decoupled, which is, by the way that software has been forever, right? Like we've got compilers and we have languages, but you also have runtimes. And once they're decoupled, they can evolve totally independently, which has been the case here too. So I think it's a very natural systems level decoupling. I also agree, like, when I do hear about P4, a lot of it is just for this, like, I want to describe my forwarding plane. Let me deal with the forwarding plane, not you deal with the forwarding plane. And so I would say that this is kind of a benefit of the architecture.
Hey, one question. So you mentioned this idea of building your system in such a way that you can just throw compute at it and then we'll scale compute. And
Yeah.
I'm curious, how much further can we scale things, and are we running out of energy?
No, it's not energy. It's not energy. So, yeah, no, we're not running out of it. If you actually look at like the energy, but I can talk about this forever, so you're going to probably have to stop me. But like, so if you actually look at the energy requirements, so the next data center is going to be gigawatt data centers. If you look at that relative to global energy, it's nothing, right? I mean, now getting it in one place is hard, but we know how to do that. A bigger issue is actually cooling. Like we need water to cool. Actually, it seems, unless you're like up in the permafrost up in Alaska, that you actually have to use deep ocean water. Otherwise, you basically kill any fresh water body. If you're trying to you'd actually raise the temperature. So but even that is not the issue. So here's what I think the issue is. For general language models, you're using language tokens, right? So one way to think about it is we as a species have been writing language for 3,000 years? So you've got 3,000 years worth of tokens, and we're within a factor of 2 of having consumed all of those. Now the scaling laws are exponential. So to get to even have the same gains that we did previously, you have to do 10x. So we're within one model size of running out of tokens. And one of the dirty secrets about language models right now is the way that they get gains now, they literally pay people to like create training data. That's about 50% of the training costs. Is like, I'll go have somebody write a piece of code. Like I'm recreating Stack Overflow. It's like almost like an arbitrage of VC money to have people create new data sets. But if you look at the dollar value for the data sets, it's actually very expensive. It's actually dwarfing the model cost. And so the bigger issue is like, we actually don't have generalized language data and we don't know how to get it. And there was this belief, but this is where Shannon comes. There was this belief that like, oh, these things are, we give them language and then they're so smart and there's these emergent properties they can reason. At this point, it's pretty clear that's just not the case. These things are basically doing fuzzy matching. They're doing it over the existing corpus. They're totally constrained to the existing corpus. It's just the corpuses are so large, they seem kind of magical. And nobody knows how to synthetically create language data. Like, what does that even mean? Like, I can synthetically create a program and see if it works by compile it. I can synthetically create simulation data, but what does it mean to synthetically create like a language? And so I think that the data problem is a real problem right now. Honestly, so seriously, so right now it's so funny. So I know what these companies are doing because I'm on the board of a lot of them. They're literally like going to old libraries. I'm not kidding. That's what they're doing. And so it turns out, by the way, so what you could say is you could say, well, there's people on the internet and they write tweets all the time. Like the marginal value of that tweet is zero, right? It's like, I guarantee 5 million other people have said that tweet before. So the marginal value of like internet content is zero. But it turns out if you got that Tibetan scroll where some dude was like meditating for 5 years and then wrote down 3 lines, like that's like, there's a lot of processing went into that. So I always view these LLMs as it's like reasoning caches. Like we've got these amazing brains and they see the world and we do all of this reasoning and then we write something down. And then it's a cache of the thing that we wrote down. But like you need to like get to the cache of the knowledge that like a lot of reasoning went into, which is kind of these old textbooks and scrolls and stuff. So that will be the next. But again, factors of 10, this group does, factors of 10 are hard. So if like, we're basically out, how do we get 10 times more? I actually think we're going to see a massive, massive decrease, which is, by the way, why they're now going to like doing planning at inference time, which is just throwing compute at the problem for planning, which is very inexact. So I think the thing will slow down quite a bit.
I just wanted to make a comment.
Yeah.
As a networking person, I heard something like that long time ago. We are running out of IPv4 addresses.
Yes.
So yeah, I just wanted to make a comment.
Yeah. Listen, there's 2 things that are simultaneously true in systems, right? Thing number 1 is everything is a sigmoid. Everything. Right? And thing number 2 is technology always advances. And we as a group have to hold that dichotomy in our heads. Yeah. But I appreciate the comment.
Just a clarification on the idea for reliable transport for Gen AI.
Yeah.
So with TCP, we have very clear signals, loss, symmetric stuff, delay and stuff. Are you thinking on terms of a response coming back and being somewhat incorrect or getting lost, or what are the properties you want to?
Yeah, so let me give you very specific examples. Okay, so my hobby is I take old video game tile sets, like from like 16-bit, 8-bit video game consoles, and I recreate those video games in JavaScript, and then I use LLMs for like the MPs and stuff. And so let's say I've got an LLM and I want it to generate a game object. It has to be correct, and I'll give it a schema. So it has to be correct JSON. It has to go to a schema, and then I want to actually have the LLM insert that into a database, right? So I can 100% determine whether the JSON's correct automatically, right? And if it's not correct, I'm going to have to reprompt it. You can absolutely determine if there's schema adherence. And again, and by the way, there's no way to evolve the prompts out. The best thing you can do is kind of retry, try harder. There's a few things that you can try to do it. And then I can also determine if like a database update works or fails, right? And so a lot of the things now for sophisticated LLM usage actually has verifiable stuff on the output that you do have to retry. And for whatever reason, wait times also increase a whole bunch if you've got a bunch of, let's say if I'm running my own API endpoint and I've got a bunch of clients that are using it. So then I have to do quality of service, and I have to do like you can have half opened, like, I mean, it's just classic web server stuff where you actually have to do a lot of resource constraints. So you have, as far as I can tell, most of the same things you have with dealing with an unreliable link. The only thing that you can't test is maybe the name of my game object is gobbledygook, right? That we have no formal way of testing that. But like if I'm building an app that creates game objects, it doesn't matter. That a human being will deal with that. And so it's all of the other stuff.
Thank you.
Yeah.
All right, I have one last question to bring us home. So you started your career working in security.
Yeah.
And now we've 20 years later, we've made networks kind of fully programmable, and we've got generative AI.
Yeah.
I know there's people working on AI for attacks and AI for defenses. I probably hate to make predictions. Probably always ask me predictions, but like, how do you see the security space advancing with all these disruptions?
I don't think it really impacts it, honestly. I mean, I've been on the forefront of a lot of these AI existential risk assumptions and policy discussions. There's something about AI that's like this endemic weakness in human beings that goes back to the Promethean, right? And it's just because you're using the word AI that people think about AGI and they think about recursive self-improvement, all this stuff. And like none of these systems have it. None of them, right? And it's just, unfortunately, it's more of like a kind of a semantic issue. And so, I think,
but just about, I think it is, I think I don't have quantitative data here, but it does seem like, we put more and more stuff online, our light bulbs and our houses and security is getting worse. And so that's separate from AI.
Well, let me counter this. So again, old guy here. So I remember when the internet was starting to get, pretty big. And there's a number of things about the internet that were like really significant when it came to this question, right? Every sociopath is your next door neighbor. That's kind of scary, right? You had new types of attack vectors. Remember the Morris worm? I mean, I do. Like it literally took out critical infrastructure. A lot of worms at CodeRed took out critical infrastructure. And then there's this thing that's kind of less relevant to like the layperson, but it's very relevant to nations, which is you have this notion of asymmetry. So with the doctrine of mutually assured destruction, I've got nukes, you've got nukes, we don't attack each other. But it turns out with compute infrastructure, the country that has more of it is the most insecure, right? So you've got this kind of notion of asymmetry, which is like, listen, if you're a country that relies heavily on it, you're going to be the most vulnerable. So even if you invest in it, you become more vulnerable. So there are three things that were massive doctrine changes around security, right? You have new threats, you have a new connectivity model, and then you have this notion of asymmetry. And yet, we kind of sensibly made our way through that. And I think that would be a much higher step change. Here's the biggest threat. The biggest threat is because AI scares people and people are just inherently kind of like worried about vague things. We're having another epoch where you're going to have a big build out. Like the internet brought down the marginal cost of distribution. AI brings down the marginal cost of content creation. So you're seeing this massive proliferation. You have none of these issues that we did with the internet, but people are somehow equating it in the same way. And so it's almost as if like they're going to regulate it before it comes out, even though like there's no indication that we should be doing that. And I'll leave you with one story, which is, it's going to sound kind of a little glib, but like I mean it, which is when I first came to Silicon Valley, like I came from a small town, like, I was here, and Linus Torvalds was giving a talk in Moffett Field. And this soon after 9/11, and I went to this talk, and this guy was just kind of this god, and I was this kind of small, village kid. And he said, it's after 9/11, he goes out on the top of this podium in front of this huge audience, of Americans. He's like, listen, like 9/11 was really bad. He said, but like there's bigger things that are worse. And I'm like, wow, who is this guy? This is terrible. He's going to get booed off the platform. He said, right now there's a number of, regulations and policymakers that are trying to make open source so that it's not free speech, that are trying to regulate cryptography, that are doing export controls or compute. He says, in the long term, those things are going to be more damaging than what happened in 9/11. And like, that had such an impression, because I'm like, dude, who the hell is this guy, man? Like, that takes some brass, like, to have that conversation for sure. But two, like, there's no way that that's the case. Like, I will say, 25 years later, he was 100% right. At the end of the day, is like the foundations of like innovation are very, very important to protect. And I think that the biggest risk, it's not some, like the threat model is going to change. It's the fact that like we as a nation have kind of forgotten that lesson, and we're going to have to learn it all over again and have an entire new battle on it. So.
All right. So on that cheery note, let's thank Martin for his time. I really want to thank Martin. Obviously, has had a tremendous amount of success in all phases of his career, and I love that he is always so generous. So if you ask him to review a paper or come to a conference or sit in a fireside chat, he always says yes. So really appreciate coming to talk to us. And,
Yeah, great. Happy to do it. Thank you very much. Thank you, everyone.